Okay, this is the third video involving calculus. This one's going to be summations and series approximations. These are two techniques that one does see a lot in physics. So let's get started. Okay, summations, particularly symbolic summations, do come up in physics, primarily in statistical mechanics. So let me start with some basics. And again, this is something that you can extract straight from your expressions palette. So let's say we want to do a sum. This will be our first sum associated. We just want to do a summation, so I'll just click on the summation button. And now it's a matter of just tabbing to each element. So n will go from 0 to infinity. Okay. And let's say the expression is 1 over 2 to the n power. Okay. So we're going to sum that up. What is that there? Just hit enter, and it will do the calculation very, very quickly. It will even do it, the symbolic, even if it's to a limit that is undetermined. So we'll click on this icon for the sum, and we will go from n equals 0 to some integer value. We'll call it big N, and we'll say it's exp of minus n. What is that expression there? It's that. And again, an expression that one does see in occasionally in statistical mechanics or quantum mechanics. It's a lot easier to get Maple to do it for you. I should also point out is you can do these types of calculations where you can give it some sort of assumptions to help it out. So if my integral or my summation happens to be this one, tab n from 0 to infinity, okay, of a times r to the n, this thing is going to blow up unless r is a very, very small number. In fact, really less than 1. So if I tell it the absolute value of r is less than 1, then this summation will not diverge, but will converge. And there is the expression there. Okay. Obviously, the other way to do it is to use the sum command. So I can go back and I can rewrite sum1 as the sum of 1 over 2 to the n. And then now I just tell it the variable n is going to be starting in the interval from 0 tab dot dot to infinity. Okay. And it will do that calculation. Or the next one, sum of my exp escape of minus n, again, comma, the variable that's changing is n, the first value is 0 dot dot to capital N, and that is the interval in which it's going to, and actually in this case it's a range because it's discrete values, and there's the expression there. Okay. The last way, of course, one can do it is to make sure it's set up properly. So if my summation happens to be something where my function is like 1 over 2 to, let's see, what do I got? How about 2 times n plus 1 quantity squared? All right. And I want to say, what's my function sum3? I can use capital sum, again, the inert version of f of n, and goes from 0 to infinity. Okay. And it will set up the inert version. I know it's the inert version because it's grayed out here, so it hasn't actually done the execution. So what's that value? Just ask it for that value, and it's there. Okay, see if you can reproduce what I've done. Okay, sometimes you'll have some data and you'd like to sum it up. This process does work. For example, here is a list of data points, list of numbers. And if I say sum the data, and I tell it essentially the elements start with element entity number 1 to entity number 6, it will sum it up as well. What's probably more useful, particularly with sequences, is to use the add command. So if you add data, it will recognize that this is a list, and it'll go through and do it all at once. And you don't have to give all the rest of this information. Sum usually works for most things. On occasionally, particularly with sequences, lists, vectors, things like this, you may need to resort to the add command. okay, our add function. And so I give an example where add fails, and I give another example where sum fails. And basically the best practice is try to solve your problems with the sum function, but occasionally you will need to move to the add function. Okay, here are some classic examples, and I'll see if you can do them. Pause now if you want to try it out. And if you want to see the summations, there is the summation there. I'm actually going to use what's called the upper bound function, which is great, which actually will tell me the number of elements, for example, in my data for problem number 2. This will allow me to calculate the mean, and then I can actually, again, use the add function here. This is where it's probably most useful to add the terms up rather than a symbolic summation. Okay, and here again, n is a value. Let's move on to something else. Okay, the next topic comes up quite a bit, and you'll see this a lot in statistical mechanics, quantum mechanics, even classical mechanics, and that's the polynomial series approximation, and getting used to generating series from following functions of polynomials is very, very useful. We're going to use two functions here, the series function to actually generate the polynomial, and then we will need to actually convert it into a polynomial because this will actually leave it as a series with some terms that are not yet defined yet. The idea is that if you have a function, and you may have heard this is called the Taylor function, or a Taylor series, I'm going to call this just series, is that any function can be approximated as a polynomial up to n number of terms if you take the derivative of this to several terms, evaluate at some point a, and then this is going to be approximation of the function near the point a. Okay, and so let's go and we can do a few examples here. All right, so oops, didn't finish that off. Let's restart here. Okay, so let's start with a function. For example, our function is pretty straightforward, x times exp of minus x squared. This is a function that comes up so often, that's why you get to see it here. So what do I do in order to create a polynomial series is, here we go, we will call this the P series, and I will use the series command. I don't know if there is an icon for the series command, series function, but basically I'm going to give it the function I want to do it. Okay, I want to tell it around which point I'd like to take the approximation. Now, if you say x equals 0, this is often known as the Claremont series. I don't remember names, doesn't matter. The key is it's around some location. So let's say we choose 1/3, all right? Okay, and I want to have so many terms in my polynomial, so I'll put 4 in. Okay, so this looks like quite a mess, but basically if you can see what's happening here is, in fact, I'll make this a little smaller to me. There is a constant we can calculate. There is a constant times the x minus 1/3 term, then a constant times the x minus 1/3 square term, then a constant times the x minus 1/3 cube terms. And then there is an order of x minus 1/3 to the 4th power. So this is the series approximation, and it includes higher order terms. That's what the O tells me. Okay, but what I'd like to do is I usually like to convert it into a polynomial. So what I need to do is to convert my P series into a polynomial, and I'll make this a little bit larger so you can see that. And when you do, is now it doesn't have this reminder that there are higher order terms. So there's our polynomial, and you might say, well, this looks pretty useful, and it's maybe more complex than you think this expression is, but at least this is something that's relatively easy to differentiate, as opposed to this one's a little bit harder to differentiate. And that is why we do these types of approximations. Most of the time, we only need about a couple of terms, okay? So how does this compare to our original function? So let's do the following. What we'll do is we will plot, open square bracket, f of x and p, so there's our expression, because it's an expression, it's not a function, from x equals minus 3 to 3, and we will make sure we put a legend in, and legend equals, and the first element is our f of x, and the second element is our approx. So how does this look? And it looks just like that. So there's the approximation. That's y. Okay, let's make this a little bit smaller here. We can zoom in a little bit. Oh, instead we'll go from -1 to we'll go from -1 to 1. And as you can see, around 1/3, my blue approximation looks pretty close to the red function itself. And in this term, then you can do much easier math. Okay, I'll pause here to let you see if you can reproduce what I did. And if you want to test yourself, here are some practice problems. So pause if you want to try it out. And let's expand the solutions. There's the function, converting it, the series of the function, evaluated x equals 0 for 2 terms as a polynomial. And interestingly enough, only 1 term comes out of it. And then using the unapply, I can actually make a function out of it, and then I can plot the 2 around essentially around the same point. And in this particular example, actually, the approximation, which is just this, a constant times x, is way easier and simpler than this whole expression. And yet it's very good approximation within 10% of essentially x equals 0. Finally, for those of you who are working with Professor Landsberg, he uses a perturbation approach to polynomial approximation. And I go through the derivation so you can see how the math people do it with the series, and how using some conversion techniques, you can turn it into the type of expression that Professor Landsberg is going to use as a perturbation formula. Okay, and in fact, we build a formula. This is very useful, again, in statistical mechanics. And that's for now. That's basically all of single variable calculus that you'll probably ever need to use in physics, even though you spent an entire year plus probably learning it. Yes, it's all done in 3 videos. The next 2 videos will be on how to do basic statistics that you would do in a laboratory or in terms of measuring any type of data. Hope to see you next.